Here's a nice one. So we got our vent connectors, and that 6 inches is straight horizontal. It's not an arch that comes in here, all right? It's going straight out to the side. So this is okay, is what we're looking at. So I got my I-joist. I'm 6 inches away from my vent connector. I switch over to my B-vent. I could get within 1 inch. I don't see any issues with that one. Here's another one. You can see that now I'm going to be within 1 inch from my B-vent to my vent connector. And actually this is above the I-joist on this one. So because it's above, now I have to maintain a 6-inch clearance between these two items. And again, that's going to be a problem. Oil connectors. This drawing is saying 18 inches. That's an apology of me. All right. Those numbers that are written on there are incorrect. Oil is going to be 9 inches. Wood will be 18 inches. And an L vent is actually also 1 inch. We're going to get off that slide real quick so there's no proof of my mistake. Vent connectors as we come off the top. Now, people have enlarged and reduced these pipes, and there's some manufacturers that do allow for it. And the only way you're going to know that is by finding the installation manuals where it comes to it. But as far as a good general rule of thumb is concerned, they should be the same size as what's coming off of here. What usually happens is that somebody they'll have an old natural draft furnace, and then they're going to put a mid-efficiency furnace in there, one that uses or exhausts far less BTUs up and out the pipe, so it doesn't have that heated draft that keeps it going. And they don't change out the actual vent connector or the B vent going outside. So the code does say that we have to size the vent connectors and the vents and the flues to the appliance or appliances. All right. So the more BTUs, the bigger it needs to be. The smaller the amount of BTUs, the smaller it needs to be. If I take an old furnace and remove it and switch out a new one and try to use the same flue chases or same B vents, it's probably not going to work. It may work. There's always a reason that something does work or doesn't work, but most likely it's not going to work. So what we're going to be looking for when we get in there, if this has been in place for a few years already, then we should be seeing some signs of condensation flowing back down. So you'll see that efflorescence. You'll see some signs of scorching that comes back in there, rust that comes in there. These are all clues that I'm not venting properly. Even with the old natural draft furnaces like we're using this one, if we would put that into an old clay tile line chimney and the vent connector would go into that, just about every furnace that I've ever seen, I haven't run into one yet, where they say that you could go ahead and put a mid-efficiency into a clay line flue. I haven't seen one model number yet that says that it's okay. So every one of these things should have a flue liner in them. And so instead of discharging into the clay line flue, I should have either a stainless steel or an aluminum corrugated flexible piece of metal that goes into that opening and goes all the way up. And again, when I size it, it should be sized to the appliance. That opening that we're showing up here on the appliance right up above the dot, that is what the manufacturer says should be the vent connector. So in all reality, that's the size it should be. Again, we shouldn't get bigger, we shouldn't get smaller, all right? And this is for mid-efficiency furnaces. Here we're showing two different appliances going into the same chimney. And a lot of this, again, is changing. This is going to be for a natural draft furnace and a water heater. We had enough BTUs to go in there originally. Once we either abandon the water heater or once we go with a higher efficient furnace, we're not dumping as much BTUs in there, and we really should be having a liner. But if this is still the original setup and that's how it was done and that's how it was designed, What we're trying to get out of this slide is the lower BTU is above the higher BTU. So the water heater should enter the chimney higher than the furnace does. The purpose of that is so that it helps create a Venturi effect and keeps all the drafting working. This is a common sense one. We have the vent connector going into the chimney. The bigger pipe is for the furnace. The one above it is for the water heater that goes in there. You can see how the mortar is missing. There's openings that are in there. We don't want to leave a chance for any of those bad gases to come into the house. That needs to be sealed up. Yeah, you keep these pipes, the bigger pipes, and you start using them on the more high efficiency units. There's a lot of condensation, a lot of moisture, and if I'm not drafting that out, moving it quick and getting it out of the house, it just starts to rust and corrode these pipes. You know, this to me was, again, another obvious defect. We see a big corroded hole in the vent connector that's just spewing carbon monoxide into the house. Nobody was going to argue with this one when we called it out. So when we see the liners inside the flue, the orange pipe that's coming up, that's the clay liner. In our area, it was very common that the round ones were used for the gas appliances. The square ones, which are bigger, were used for wood fireplaces and such. But again, once I put in a higher efficient furnace, so a mid-efficiency forced draft unit, or if I abandon the water heater, again, I don't have, if I had a 100,000 BTU furnace and a 40,000 BTU water heater, and now I put a high efficiency, so I direct vented my furnace, I only have a water heater going up there. Now I only have 40,000 BTUs going up there. That needs to be brought down to the right size. And then from the top, we should be able to see some sort of a metal pipe and a cap to prevent rain from coming in there. That should be installed. Sometimes you'll see a flat piece that goes over the top of the flue, and that keeps the water from coming into it. And then they'll just have a standard B vent opening on top of it. So now we get into the high efficiency furnaces. And each one of these things are different. And you do have to look at the manufacturer's venting instructions, and depending on the size that they're going to be is how long of a run that you could have. Now, when we're dealing with the high efficiency ones, very rarely do I ever see these things have a problem. Those PVCs are pipes. First of all, they're designed to take the corrosion. The fans are usually powerful enough to go ahead and push all the air out. And then they are sloped backwards, not just to let the heat rise, mind you, but more so to let the condensation fall back. And then we end up collecting that condensation and we have to allow it to drain. When we talk about high efficiency furnaces, we should understand that these are also called condensing furnaces. When you talk about using a 95% furnace, all right, realize what we were saying before when we talked about clocking the meters, all right. If this is, and I'm just going to use round numbers to keep the math simple, if this is a 100,000 BTU furnace, that means that fire at the top of this screen up here, this fire is creating 100,000 BTUs. As the heat that's been created from there goes down into the primary and into the secondary heat exchanger, during all this whole process, I'm absorbing 95% of this heat that I'm creating. 95% of that heat is going through the house. Only 5% of that heat is being exhausted. I still have 100% of all the combustion byproducts. So I still have whatever carbon monoxide is being produced, whatever carbon dioxide, however much oxygen is left. That's all still in the bad gases, and that does need to be exhausted to the outside. All right. But since I'm absorbing 95% of the heat, and only 5,000 BTUs are going out the vent, that change in temperature is so drastic that it pulls a lot of moisture and condensation out of the air. Hence, that's why they get the name of a condensing furnace. I have no choice. I have to be able to collect that condensation and I have to give that condensation a place to drain. In our area, we pretty much go with gravity drains. Typically, there's going to be a floor drain nearby the furnace somewhere. If there isn't, then I'm going to have a condensate pump, and that's what they're, well, that's not what they're showing here. It's a neutralizer. We don't use neutralizers in our area so much. We just let it go right into the raw sewage as it comes in there. But it's like when a cold front comes in, we usually get rain associated with it. We get a sudden temperature drop, and then it rains. Same thing here. I change that temperature. I go from, at the beginning of that fire, it's probably going to be about 300-400 degrees where that fire is, probably hotter. And then when I leave, it's going to be somewhere around 125 degrees in that ballpark where it's being exhausted. So it might be all the way up to 1,000 degrees up there. So I'm changing from 1,000 down to 100, eating up 90% of that temperature and bringing it to the inside of the house. Just a side note, and we'll talk about it again with high efficiency furnaces. All the way on the bottom of the floor underneath here, when these things are running, we want to peek underneath there and see if they're dripping. A lot of times we'll get a hole or a crack in the secondary heat exchanger, and since that's the lowest point, that condensation is going to collect there, and if there's an opening, then it's just going to drip straight down to the floor. It's a pretty strong indicator if I have water dripping on the floor that I got a hole in that secondary heat exchanger. All right. Same thing though, we still want to be 1/4 inch per foot vented up and away. But again, it's not so much to let the heat rise as it is to let the condensation fall back. Here's our typical high efficiency 2-pipe system. On this one, I believe we're drawing combustion air in from the top. That's that middle pipe up here. And then we're exhausting combustion air out this way. All right, so the fan is here, and that's blowing the air out there and creating our pressure differentials. We can use this type of furnace and draw combustion air from inside the house. We have to go back to those room sizes and fresh air for the combustion air coming in there. Me personally, I just think it's a waste of time and energy if you're going to go ahead and do that. One of the nice things about these things that makes them 95% efficient as well is I don't use any of the air that I've already conditioned or any of the air that I've already heated to go ahead and make a fire and blow that air to the outside. I'm bringing in outside air, using that to make my fire, and then I just keep my indoor air, If I disconnect that combustion pipe from the outside and I start using inside combustion air, now I'm taking air that I've already heated. I've already paid to heat this air. Now I'm using that to go ahead and make, using it as combustion air, and then I'm just going to exhaust it outside my building. And that has to be brought in and replaced. And where does it come from? It comes from the outside, and now I have to heat that air again. So that reduces the efficiency. I have nothing to back this up, but in my opinion, if you bring combustion air on a high efficiency furnace, it's the same thing as being an 80% furnace. The amount of air that flows through there that you're using for the fire and blowing back outside is, you might as well just buy an 80%er and leave it at that. But that's just my 2 cents. I like to see both pipes being used when you can. Discharging the high efficiency furnaces, we have to keep them away from windows, soffits, anywhere where that carbon monoxide gas could come back into the building. They have to be stayed away from the gas meters, outlets, doorways, walkways, and so forth. Surprisingly, most of our clearances are actually pretty small. We don't have many furnaces that are going to be over 100,000 BTUs. So most of our vent connectors, and it looks bad, but most of them could be within a foot to an openable window. All right, if it's over 100,000 BTUs, then it needs to be further away. Being above the grade, I would always take in snow issues, especially for the combustion air intake. I think the exhaust, it's going to more or less melt everything when it comes out of there, so I'm not too worried about that one. But the air intake, if that's covered with snow and I can't draw combustion air in, then my furnace isn't going to start. They have pressure differential switches in there to keep it safe. Improper, so if we're right next to a window, obviously too close to the ground, below the window, less than a foot, these are all going to be things we want to look for. And again, it's only 12 inches. And so we're talking about the discharge and not the intake. So on these two, we have two different furnaces. What's folded downwards, that's my exhaust. And then what's pointed straight outward, that's my, I take that back, I'm sorry. What's pointed straight outward is my exhaust. And what's pointed down, that's my intake. I got those flipped around, it comes in there. So that exhaust, as I'm blowing air away, that's what needs to be a foot away from those windows. And yeah, I think I'm close, but I don't think I'm close enough to where I'd call these out. And the other thing is, when it's new construction like this, typically they're not done wrong. We're going to have a code official, but nonetheless, we're not going to rely on someone else's work. They're paying us to do our work. We should know the rules. 1 foot is our magic number. Now, when I start seeing a whole lot of hokiness that goes on here, not sure what's the water heater, what's a furnace, what's a sump pump discharge. I mean, we could probably figure all that out and take pretty good guesses at it. Water heaters are typically going to be bigger. The furnaces are typically going to be paired up, and I'm guessing we have 2 sump discharges here, but just being over that basement window, I would have an issue with that as well. And if this is a sump discharge here, yeah, I don't know if that has enough oompa to get past that window. And then if this is a water heater discharge here, I think I'm blowing that right into that window well, and that would cause it to come into the house. So, yeah, anytime I see stuff that's messy like this, I get a little panicky and a little nervous, and I just start taking pictures and diagramming everything quite a bit better. What we're seeing now is single pipes coming out of walls, but it doesn't look like there's a combustion air pipe. So we're just doing exhaust. And that may be true. It may just be an exhaust only. But in this situation, it's not. All right. If you can see, there's kind of another pipe in there with it. So what happens is they put a pipe in a pipe, and there's special fittings to make that work. So we're exhausting out the middle. I'll go back. All right. So we're exhausting out of here. But then right around the outer rim is where my combustion air is coming into. So even though it's only one pipe, we're still doing both different things. We're bringing combustion air in, and we're exhausting gases out. And how we do that, this is what it looks like on the inside. So this pipe up here is my exhaust, and this one down here is my combustion air intake. Other clues on the outside that this is happening is, and this is what I actually have on my house, you'll see the cone-shaped ones. So the area behind here is where my combustion air is coming in. And then, of course, my exhaust is coming out of the point here. So I still using both pipes, even though I'm only seeing one on the outside. The flat panels, same thing. Around the outside edges, up here is where we're drawing in our combustion air. And then our exhaust air is going to the outside. When they started bringing in high-efficiency furnaces, and there were a lot of condo buildings and these high-rises in the city, and they're like, well, everything we have here, we have vent pipes going through the middle. What are we going to do if these things have to be sidewall vented? We don't want to have a whole bunch of pipes sticking out of our building. It's going to look horrible. So they started making things a little bit more attractive, and I don't think these things are too bad looking. And they could be painted. So here's a typical water heater. I have seen them glued. For the most part, though, I usually see a pressure clamp around these things so that that'll cinch up on it, and it could be removed when I have to remove the water heater. It just makes life a lot easier in the future. But yes, it can end up being glued. I know I found a video, and I lift up on these things just to see if they are secure in there. I mean, I do have a fan that's being blown on there. If it's loose and not tight around it, then yeah, I'm going to roll the dice and take a chance of carbon monoxide being blown into the building. But more so, it's the other way around. I don't want somebody sending me a video of saying, why didn't you tell me that this thing's not connected? So I just lift up on it and make sure the pipes are secure. I know this isn't really about heating, but again, different appliances, we vent them in different ways, and a dryer is an appliance. They do have different types of ducts that could be there. At no time are we allowed to use a plastic duct for a dryer. At least if it does exist, I am definitely not aware of it. All right. I've seen the soft foil types. I've seen the hard foil types. So these are the hard foil ones. Most dryer manufacturers, they call for these hard metal ones, and I've heard a lot of home inspectors, they're kind of adamant about it. They want these hard ones to be there. I've seen the foil type ones, and I don't believe I have a picture of it. I don't. I've seen the foil type ones. I actually don't have a problem with those. So I think I'm in the minority with it. But again, we're all entitled to our own opinions. The foil ones, they are UL listed. All right, so they are tested and proven to work with all the different ones. But most of the dryer manufacturers say that we don't want those foil things on our dryers. So they're the ones that say it's not a good idea. Me personally, I really don't have an issue, and I don't call them out. I actually like them better with these hard ones like this. I've seen people push their dryers back, and then they end up smashing the pipe. And once you do that, you got to kind of throw it away and get a new pipe. With those foil ones, if you smash it, you pull it away, it kind of springs back to normal. So that's another thing I like about it. These are a little bit smoother, so they don't collect as much lint inside of them. Where the foil ones, they're kind of corrugated for far rougher than what we're seeing here, and they are known for collecting a lot of dryer lint. And if it gets clogged up, the dryers, they just keep pumping along. The only clue you're going to get is that your clothes aren't drying as fast. But yeah, I don't know what else to tell people. I'm not a fan of cleaning the vent connectors. And you know what? I'm using the term vent connector, and I'm using it wrong. These are called transition vents. So, and these are also not allowed to go through the structure or through a floor. Typically, I believe they're 6 feet max in length. But the dryer vents, which are smooth walls, some dryer companies say you can go up to 50 feet on the smooth wall ones, but not with these things. Here we're just showing where it's a small smooth wall line that goes through a wall, and then the transition vent is what connects it from the vent to the appliance. Anyway, I think I babbled enough about that. I'm okay with the foil ones. You're going to have to make your own call on that one. All right. Thermostats, and then it's what turns the furnaces or hydronic boilers and so forth. It turns them on and off. It's really nothing more than an automated light switch, for lack of a better term. When the temperature drops down below the desired amount, then the thermostat flips the switch on and the furnace turns on. And the furnace stays on. It keeps running and running and running and running until the thermostat says, okay, I'm warm enough, and then it turns itself off. Nothing more than that. It doesn't adjust the fire, doesn't make the fire burn any hotter or cooler. A furnace does what it does, and that's all it does. All right. Humidistats is basically the same thing, only it uses its humidity sensors to turn the humidifier on and off. So that's also a switch. The isolation or equipment cutoff switch, We should find that within reach of the furnace, and that's so somebody can work on the furnace and turn the power off to it without taking a chance that the automatic thermostat automatically turns the furnace on. So a few basic, I think they're kind of common sense rules. Older thermostats, the ones that had the little mercury bulbs in them, older ones, they need to be level. They need to be straight up and down. I'm not too sure, and I don't believe it's the case, when you start getting into the newer ones, such as the Nest and the Ecobees. You know, those have different sensors inside of them, and they could probably be put on an angle and still be working fine. But in all reality, everything should be straight up and down. We also want to look at the location of those devices. They shouldn't be in direct sunlight. They shouldn't be having a heat blowing on them or air conditioning blowing on them. They shouldn't be near a refrigerator or a stove or any other appliance that's going to be putting off heat. We kind of want them in the center of the area of the heat that we want to control, so not on outside walls or drafts. And if you think about it, why would I want any outside influence on that thermometer to be able to turn this thing on and off? All right. So old school stuff, the old coil thermostats with the mercury bulb in there. And basically, it's a piece of metal that works off of the principle where when something gets hot, it expands. When something gets cold, it shrinks. So if I take that piece of metal and I spin it around like we're seeing here, as it gets cold, it's going to rotate and start to close. And when it does that, the mercury ball is going to slide over and basically close the switch or the contacts on there, and that's going to turn the furnace on. And as the furnace is operating and gets the room warmer and warmer, this thing is going to want to uncoil at that point in time. And when that happens, then the mercury falls away from the contacts, and the furnace is told to shut down. Plain and simple. Just a nice on-off switch. Mercury was found to be bad for human beings, so we started getting rid of it. There it goes. Nowadays, what we're doing is getting into the magnets, and we're getting rid of the mercuries, but it's still the same principle. All right, so that coil comes down, reaches the other magnet. Once it gets close enough, it pulls them together, in which case it pinches or closes the circuit and turns it on. And as it heats up and gets hot, it tries to expand enough where it breaks the circuit and causes everything to close. Sorry about that. Anticipators, they're able to tell how fast the temperature is rising and how long the furnace needs to operate in order to reach that number, so it actually turns the fire off sooner and then later. So getting back a little bit, when the furnace is operating, we have a fire inside the heat exchanger. The heat exchanger is the metal part that keeps all the bad gases, keeps the fire, keeps that contained. The metal gets hot itself, and then we blow air around the metal in order to absorb that heat that's passing through conduction. We absorb that heat and bring it to our rooms. When the fire goes out, that piece of metal is still hot. That's still usable heat. All right. So we're going to keep the blower fan blowing air, absorbing that heat from the metal and bringing that heat into the house. This anticipator anticipates how that's working, and it says, all right, we're going up 1 degree every 5 minutes, and we're going to shut the fire down, and we know that we'll have still 5 more minutes of heat. And of course, I'm making up numbers. But it anticipates and it shuts the fire off early before it reaches the desired temperature, knowing that there's going to be enough heat in the heat exchanger to reach that. And that's all programmed with everything together.